Well, hello, my friends. Welcome back to Digital Discovery, where we examine an introduction to calculus. In this series for Section 3, we're going to examine the topic of the derivative. The derivative is the rate of change in a curve, and we will develop that definition. We will establish methodologies for determining the derivative. We will look at the utilization of derivative rules, and then we will use the derivative to solve real life problems. But in this video, we start simply with the question, what is a derivative? The derivative is defined as the rate of change for the curve where y equals a function of x. You notice you have a curve. Y equals a function of x means that every x maps to one y such that the point xy is on the curve. Now, in other words, no x can map to two y values. So y is a function of x. Look at this again. x1 maps to y1. It is a function because each x maps to a unique y, and together these two create an ordered pair of a point which is on the curve under the definition of y equals a function of x. Now, we notice that y equals a function of x, y and f of x can be used interchangeably. In other words, instead of having y1, x1, and y1 can be written as a function of x1. F of x and y are the same values and they are totally interchangeable. Now, let's go back to this curve just a moment. How many points are on the curve? Well, the answer to that is infinitely many. I just simply located a few points that are all under the curve under this definition where when we plug an x in, it leads us to a y such that the ordered pair is on the curve. Y is a function of x. There are infinitely many x values, therefore there are infinitely many corresponding y values, and there are infinitely many points on the curve. That's important that we recognize this because it presents an interesting problem as the curve is ever changing. Notice these 3 points that I've identified. We have x1, y1, x2, y2, and x3, y3. The curve rate of change is often referred to as the slope of the curve at a given point. At each one of these points, we have a unique slope of the curve. And let's see if we can define that a little bit. In order to find the slope of a curve, we're going to use ideas relating to the slope of a line. We use a line in calculus, which is said to be tangent to the curve. That means in the local region, it only meets the curve at one point. And the concept is that if this line goes through this point and the line is tangent to the curve, then at that point the curve and the line have the same slope. And if we can find the slope of the line tangent to the curve at that given point, then we can find the slope of the curve at that given point. Notice that tangent means it touches the point of the curve at only one point in that local region. Now, the line tangent to the curve and the curve have the same point. Let's go back through these 3 points. Here, the line tangent has a relatively mild positive slope. It's a little larger in this point, but then it's negative here. It's very interesting to see that the lines on the curve each have a tangent line, and each tangent line may have different slopes. So the rate of the curve is ever changing. The slope of the curve is. Now, in order to develop our methodology, let's go back and let's work on the slope of a line. Just a basic line going through any 2 given points. The line as a function of x is defined by y equals mx plus b, where b is the slope, is the y-intercept, where it crosses the y-axis, and m is the slope. You notice that each one of these points, x1 and x2, generates a unique y value, y1 and y2, such that those points are on the line. B is defined to be the place where x is 0. That generates where y is b under this definition, and b becomes the y-intercept, where it crosses the y-axis. So the slope then is defined to be, for these 2 points in algebra, y2 minus y1, and x2 minus x1. This is described to be the change in y divided by the change in x. A lot of times they will call that the rise over the run. Delta y over delta x is defined to be the change in y divided by the change in x, which is the slope. Now notice that if we take y2 and we subtract y1 from it, we get the change in y. And if we take x2 and we subtract x1 from it, we get the change in x. Here is the rise over the run. The change in y divided by the change in x. Delta y over delta x. Now let us examine the concept of derivative by taking this picture and by making it a little bit larger so that we can work with it easier. The derivative is the slope of the line tangent to the curve. So the derivative is the slope of the curve, but the slope of the curve at that point is the same as the slope of the line tangent to the curve. So we say the derivative is the slope of the line tangent to the curve at a given point. Now, the tangent line and the curve have the same slope. Let that sink in. The tangent line and the curve have the same slope at this point because this point is on the line. And all the points on the line have the same slope. Now, let's see if we can develop a methodology for finding the slope of the tangent line. Now, let's start out with this idea that we have 2 points on the curve, x1, y1, and x2, y2. Now, notice x1 and x2 here are fairly widely apart. They have a distance. That distance we will define as the change in x. What would happen if we let this change in x approach 0? In other words, we pull x2 back to the place where it becomes almost x1, then it should home in on the line, the slope of the line that is tangent to the curve. Watch what happens. We start out, here is delta x. Delta x is fairly large. We make it smaller. We make it smaller still, and then finally we pull it back where delta x is 0. So x2 and x1 have become the same point. Let me do that for you again. Here we have them widely apart. We slide down the curve with x2. We slide down the curve with x2 until delta x becomes 0. We're going to define the line, or the slope of the line, tangent to the curve, to be the limit, as delta x approaches 0, of the slope of this line. So that's going to be a really interesting definition. When we isolate the slope of the line tangent to the curve, we have in fact found the slope of the curve. We have found the derivative at the point x1 because we have located the slope of the line tangent to the curve at x1, and x1 is on that line. It's a very interesting concept. The derivative is defined as the rate of change for the curve where y is equal to a function of x. In other words, this curve is y equals a function of x. At x1, if we can find the slope of the line tangent to the curve, we have indeed found the derivative or the slope of the curve, because the derivative and the slope are the same thing. The line tangent to the curve and the curve have the same slope at that single point. Now we simply have to develop the idea of finding the slope of the line that is tangent to the curve at a given point. All of this is founded on the definition of the slope of the line. Remember that, because in the next video we're going to take the slope of the line, we're going to set it up under a definition where delta x approaches 0, and lo and behold, we will have found the derivative. The derivative is the rate of change for the slope of the line tangent to the curve. Now we will develop a methodology for finding the derivative now that we have defined the derivative. Now you thought calculus was going to be very hard. If you stay up, if you will learn each step, then you're going to be able to climb the ladder from the ground until you soar into the skies. Remember that algebra is the language of calculus. Calculus is the language of differential equations. Differential equations explains the world in which we live. It's all a matter of just climbing one step at a time. In this step, you know that the derivative is the slope of the line tangent to the curve at a given point. We wish you well on your journey. You will have fun.